Hi, everybody. Um, this talk is called IPv6 Insecurity Revolutions. The first talk on IPv6 insecurities I did in 2005, 2006. There were lots of stuff to find, but the following years I found way more stuff, so I did a second talk on IPv6 completely new stuff, and matrix style I call it IPv6 Insecurity Reloaded. So that's why this talk now has to be called Revolutions, of course, for no other reason. Did anybody here see one of my previous talks on IPv6? Hands up, please. I know that for some. Okay. For those who haven't seen one of my previous talks, this is completely new things, and I don't give any IPv6 introduction. So if you don't know anything about IPv6, you will miss some aspects, but that's life. I only have 50 minutes, and even the talk is scheduled from the content is for 60 minutes, so I have to do it a little bit faster. I'm Marc or Van Hauser. You might know me from stuff I did for SUSE Linux Security, or the Hacker's Choice, chc.org, Hydra, AMAP, and stuff like that. So I've been around for a long time, and I love to hack stuff. And actually, it's my opinion that hacking is very important actually for society, for every one of us. If there would not be hackers breaking stuff, security of the systems we will be using would be horribly bad. So my opinion is that everybody should do security research, publish it, and kick vendors in their balls, so they have to do better security in their products. So that's why time and time again I go back to IPv6. For me, actually, IPv6 is kind of boring now, because I've done so much and it's not really new stuff for me, but how should I put that? Nobody else seems to be doing that. Yeah, it's only Fernando Gond. He does the other part. So I kick the vendors in the ball, say, hey, you fucked up, this is bad, this is bad, this is bad. And he comes along, hey, I've written in RFC, this is how we should improve things. And that's how we two work now as a team to actually make things better. And it's starting to pay off. So things are going better. But there's still lots of room of improvement. So this talk is how I call a potpourri of things in security in IPv6, of all the different matters that have somehow to do with IPv6, so really completely different things. So there's nothing like a red thread or something like that in this talk. First, shortly, I want to talk about what is actually the situation with IPv6. Do we get it finally? Or can we pass the bucket and stay with IPv4? Hopefully. Yeah, I'll tell you. Then I'll talk about vulnerabilities. Of course, that's the juicy stuff. Then, who's doing penetration testing here? How do you say, paid or unpaid hobby type? Hands up, please. Okay, I would say there's about a third. What are you other guys doing here in this talk? Okay, so I will talk shortly about pen testing, because so far there's basically no information on how you do IPv6 pen testing from remote to a remote network, which is really a challenge. I show that in my trainings, but actually this is the first time I showed it publicly, and there's no other information for that available. So if somehow, for whatever reason, you doze off, you start sleeping, if you do pen testing, that's the point when you should wake up. And if I have time left at the end, I talk about, is there any hope? I don't think I will have time, so I'll say already no. Yeah, that's how it is, sorry. So, the situation. Once upon a time, in a far away fairyland, when IPv6 was designed, people were thinking everything would be good in the future. So you find stuff in the RFC where you think, okay, what were they smoking to think that something like that would happen in the future? For example, one essential thing where they were hoping that would exist is that everybody would encrypt in the future. And I'm not talking about SSL. I'm talking about IPsec. When they defined IPv6 in 1995, they thought, yeah, I'm pretty sure in 2050, when they start implementing IPv6, everybody will use IPsec already. So we should prepare for that and require that it is somehow mandatory for security that it should be there. Yeah. Now we have to introduce IPv6, and where is IPsec? Nowhere. Well, you only have it for VPN connections over the internet, and that's it. So it was done in a fairy tale time. When they designed IPv6, they were hoping for something like that. So, or that, sorry, I don't know which one to choose here. So they expected, yeah, the size of the internet will grow because more and more people get online. They were not thinking about mobile phones having an internet connection or iPads or whatsoever. So, but of course there would be growth in the internet. As there are only 4 billion possible IP addresses in IPv4, and we are already over 6 billion people on the planet, something doesn't match here. Yeah, so we need more addresses, and this is not possible with IPv4. So they were thinking, okay, this larger size of the internet, of course, the IPv4 pool size is depleting. We as human rational beings, we see that coming and react accordingly to that. So we start early with IPv6 deployment, and yeah, IPv4 is at some point not needed anymore. And then everything will be fine. The reality is this. The size of the internet is growing, IPv4, whoops, going down, and IPv6 deploying, not much. And that's our current problem. Now starting with IPv6 is actually already too late. Last month, or 6 weeks ago, RIPE handed out the last IPv4 addresses, so that now only one Class A network is left for addressing in Europe. With that, a special protocol kicks in place. You only get new IPv4 addresses from that A-class network, which is left, if you prove you're already deploying IPv6. So if you need new IPv4 addresses, you must deploy IPv6. That's why now we will start a very, very large rush of people. Oh fuck, we have to do IPv6 now if you want growth. Yeah, if you're new, if you're an old company and you grabbed a large piece of the cake, so you have enough IPv4 address, good for you, or ISP who grabbed fast enough. But if you're a smaller company, a new company, you can be in trouble now. And you have to do IPv6 fast. So the end is basically near. Because we have to do IPv6, but we're not prepared, especially security-wise. So, in every talk on IPv6, I put in this slide. And it shows, and I update it, of course, every few months. So this shows the reported number of vulnerabilities, so publicly reported CVE entries, on IPv6. The last summer from 2012, that's what's currently reported. We are about 14, but actually that's already 4 weeks ago, and I thought there were 3 more. There was someone who found 3 security vulnerabilities in DHCP v6 server implementations, but more and more is to come, because how this works, you find a vulnerability, you report it to the vendor, the CVE get assigned to the year, but it may not be made public usually until there is a fix out. And if the vulnerability, for example, if it's Oracle, this can take 3 years or longer until you can make it public. So that's why a lot of stuff from 2012 is not yet published. And I have even one open from 2011 still, and I'm pretty sure others have as well. So this is always very conservative, my guessing here. Now you might say, okay, IPv6 vulnerabilities. Of course they exist. Vulnerabilities exist in everything. So of course they exist also in IPv4. So where's the difference? Where's the risk? If you compared it with the numbers of IPv4 vulnerabilities, there's a little mismatch here. I mean, not all systems have IPv6 implemented, but everything has IPv4. So the target area for IPv4 is much larger than for IPv6. Still, twice the number of vulnerabilities are reported. which shows you one thing: there's a difference in maturity of the security of the implementation. So IPv6 is long not at the same stage where IPv4 is with the maturity of the security implementation, which means there are many, many bugs to find. And alone in this presentation, I will show you stuff for 6 more CVE entries, which I haven't even calculated in there. So I grouped them, the vulnerabilities together through some stuff, and I call them all surprises because people sometimes, so the people implementing something and would be totally surprised what could happen. That's usually hacker stuff, hackers doing something different. However, as you will also see, this is stuff which is very, very easy. It doesn't need a great hacker to come up with these attacks. Anybody can come up with the attacks. You don't need to be a great hacker. Just being a script kiddie is basically enough to come up with that. And you wouldn't believe who's affected. So flooding surprises. This is a reminder from 2 years ago in my previous talk, the reloaded one from 2000, when was that, 2009, 2010. I found a pretty simple vulnerability. In IPv6, you have a feature called router advertisement. This is a router on the network, sends this packet so everybody on the local network knows, oh, there's the router. So you don't have to do any default route configuration by hand or by DHCP anymore. So the router announced himself on network, so I'm here, I'm the router. And yeah, it's easier this way. There is an option which is called auto configuration. The feature is meant to be a replacement for DHCP, so that DHCP doesn't need to be used anymore. It's part of the router advertisement, and if this option is set in the router advertisement packet, it says this is the network prefix, you should configure yourself an IP address in, and the systems by default all do that. The vulnerability I found is if you pretend there are 1 million routers on the local network, and they all say, yes, do auto configuration on this different IPv6 address space. If it's Windows, BSD, Juniper, Cisco, they all would do that for 1 million addresses. Yeah, who needs 1 million IPv6 addresses per interface? Nobody. Yeah, but some people were surprised that someone might come up to that idea, which is, I think it's not that clever. Really, anybody can come up with that. But everything, Windows was affected, Cisco was affected, Juniper, NetBSD. And everybody fixed that pretty fast, except for Windows and Juniper. They are still vulnerable after 2 years. What's the impact? The impact is 100% CPU, 100% RAM by just flooding for about 15 seconds, and the systems are not recovering. The only thing you can do is have to turn off now the hard way. That's the only thing you can do. And affected is also Windows 8 and Windows 2012 server. Yeah, and it's not getting fixed. And let's revisit that one, because exactly the same vulnerability is present with the same culprits. Yeah, this time OS X is affected too, same thing. But this time not saying auto configuration, this time you put in route entries, which shows you that lots of IPv6 implementers or the developers who implement IPv6, they do what we in security call Indian development style. Indian development style means if you fix something, you don't look left and right if there's the same vulnerability in the ejected code, because you just don't care. Yeah, because that's not your job. Yeah, your job is to fix that bug. If there's a bug one line before or after, you don't care. You might call it racist, but that's how we call. If you work enough with Symantec and Oracle, you get fed up with how they react, how they fix bugs, how they not fix bugs, and stuff like that. So sorry, Indian programming or Indian fixing. Yes, and again, I mean, it's a simple bug. Anybody can come up with that. It's the same like 2 years before, basically, and everyone, again, is affected. Yeah? How surprising is that? There's a new tool for that, FloodRouter 2.6, which you can download from the THC IPv6 package I published 3 weeks ago. You just start it, and everything which is BSD, Windows-based, is gone from the IPv6 network. Just gone. So don't try that here at the conference. So, Um, Another thing which is so easy, it's unbelievable that it works. In IPv6, you have neighbor solicitation. Neighbor solicitation is a replacement for ARP. In IPv4, if you want on the local network the MAC address to an IPv4 address to be able to send that person packets, you do an ARP lookup, an ARP request. The same thing you have in IPv6, but it's done with ICMP instead of ARP, and it's called neighbor solicitation because it sounds cooler. So if you want the MAC address to an IPv6 address, you send a neighbor solicitation request to the network, and this person who has this IPv6 address answers with a neighbor advertisement packet which contains the MAC address. Of course, you can do the same thing as in IPv4, ARP spoofing, neighbor discovery spoofing and stuff like that. ARP man in the middle, neighbor discovery man in the middle, same thing. I presented on that 7 years ago. But the surprising is if you send thousands of these neighbor solicitation packets to one target, what happens is that that target is busy sending replies and doing nothing else. Because how it works is this is done in the kernel. The kernel gets this packet and replies to that. And because the kernel has the highest priority, higher than any user space process, that's the only thing it does. And again, you might be surprised, so, okay, who would implement something like that? Yeah, everybody. Again, it's a simple attack. Anybody can come out. It's really don't have to be a great hacker. Anybody can do that. And come on. You might be surprised, so what about Linux? I mean, the Linux kernel is not known to be the most secure kernel being developed. Surprisingly, very, very few vulnerabilities I found affect Linux. So I've tested Linux, yeah, but it's not affected. The very, very newest, however, the 3.6 has a vulnerability. I don't know what it is, but while testing the last training, so not this training I did, but the training I did 3 weeks ago, we crashed the newest Linux kernel by some tools which are on the package, and we don't know which one because we're using them all at once. So maybe you find out which one it is and publish that, please. So then, after flooding surprises, let's do fragmentation surprises. What can happen with fragmentation? There's a big difference in how fragmentation works in IPv6 than it does in IPv4. In IPv4, you just send out packets, and if there is a too small link on the path, the router fragments the packets for you, so it gets to the right size. In IPv6, this is not allowed. No router may fragment packets. The only thing a router may do is throw the packet away and send a packet to the sender saying, oh, you know, this packet was too large, please make them smaller, otherwise I can't fit them and have to throw them away. And then the host fragments the packets. In IPv6, only the host, the sender, is allowed to fragment the packets. Which may think, okay, why can he just resend and smaller packets and instead of fragmentation? So, but yeah, that's how it works. This is how fragmentation is done in IPv6. There's an extra header being put between the IPv6 header and the transport layer, TCP, UDP, ICMP, in between. It's always 8 bytes in length. It has a fragmentation offset. This is calculated in 8 byte values. So the first fragment always starts, of course, with offset 0, because that's where the packet starts. And then there's 1 bit, which is the more fragments bit. If there are more fragments to come, there's a 1. If there's the last fragment, it's a 0. So what you can do in IPv6, which is not possible in IPv4, you can put in a fragmentation header that starts at offset 0, so it's the first fragment, and you set a 0 to the more fragments bit, so it's the last fragment. Which makes no sense, yeah, first fragment, last fragment, and doing fragmentation, but it works. It's called one-shot fragmentation or atomic fragment, and it's accepted by all systems. And we can do stuff with that, of course. And then there's a fragmentation ID. This is the identifier, so fragmentation streams can see, okay, these belong together, these fragments. So what can we do with that? For example, we start fragmenting a large packet. We send 1 kilobyte of data each. So the first has offset of 0, and the more fragments bit is set. We send the second one, offset is one at 1024 bytes and more fragments. We continue, continue, continue until a very large number, 64,512, set the more fragments bit and send 1016 bytes of data. Why that? We want to go to the maximum amount possible of the fragmentation offset, which is 65,528. Now we say this is the last fragment and send the maximum amount of data, which is common on an Ethernet link, which is 1,500 bytes, minus fragmentation header, minus IPv6 header, and then you get to 1,432 bytes. Now, when this is received, the systems will reassemble the packet because now it is complete. What they get, come on, is a packet which is 66,960 bytes in size, which is larger than allowed because the maximum packet size in IPv6 is the same as in IPv4, is 64 kilobytes. This is more than 64 kilobytes. If you add to it the 40 bytes from the IPv6 header, you have 67,000 bytes. What could probably go wrong? To some, this might be a surprise that this is possible. Yeah? Actually, all the stuff I'm showing you now, all the next vulnerabilities, I didn't look for any one of these. You might ask, but how did you find this stuff? I just stumbled across it. So I had, back in that time, a Vira personal firewall in my system, and then when I was creating packets and playing around, I would always get a blue screen. This one. So I thought, okay, what the fuck? And because it happened again and again, I thought, okay, it must be this tool I'm coding. When I started, it blue screen. So why? And then I looked into it, and until I found out, okay, it was a Vira personal firewall. So any other personal firewall might be affected as well. I haven't checked. You can do that. The tools are all in the package. It's fixed with a Vira personal firewall 2013, which came out 4 weeks ago, before I did my first presentation on that. They fixed it in time. However, if you still have a Vira personal firewall 2012, it will take another month or so until they put out a fix for the older version. So if you still have 2012, you're still vulnerable. Yeah. Other fragmentation surprises. This is a Zyxel Cywall firewall, which is usually used in small, medium business environments. Because it's pretty flexible, has lots of options. As I found out, lots of the options actually don't work, but yeah. It's also not that expensive. So imagine you have a rule configured which allows SSH access to an internal machine. But hey, this time someone is accessing that internal machine on SSH. The administrator recognizes, fuck, we have an evil hacker who just compromised our internal server. Fuck, I have to change the rule to block him out. Yeah? So connection is terminated. He tries again, it is blocked. Unless you put a fragmentation header before the TCP SYN packet. Then it's allowed through. And I was surprised, so I sent him a bug report and said, hey, I found this stuff. You can bypass the ACL rule which was created. You should fix that. And they told me, no, this is correct behavior. Because as it's a fragmented packet, it must belong to an established connection, which they don't actually have. I mean, TCP SYN is nothing being established connection, but because in some history hours ago, there once was a rule which allowed something, it might belong to that old rule. So we don't want to hinder any customer experience, so we allow it through. Unbelievable. Yeah? Even if you have specifically set up a rule which denies that kind of traffic, you can bypass it. And yes, they don't consider this a bug. Yeah. Makes you ask the question if they're really a security vendor. Yeah. Other fragmentation surprises, again, this is now a Staro firewall, and it was just an innocent bystander to the test when I was doing IPv6, the small IPv6 project for a customer. It was just on the path and got hit by something which is also very, very easy attack actually. I sent a fragment ID is A, offset 0, so it's the first fragment. I send a second packet, same fragment ID, but with an offset of 20,000, and I send a third one, fragment ID A, with an offset of 60,000. What should happen? Well, they just collect these three fragments and fine. If you flood that, however, what happened is that the firewall just went 100% CPU, totally crash. And what happened there was that, oh, there's a packet which will become, if I get all the other fragments, 60 kilobytes. I should already allocate that memory. So you just flood with some very small packets, and just after 20 seconds, it's gone. Again, a very, very easy attack. And now we have firewall vendors which are not able to implement IPv6 security and can be surprised by such simple things. Packet going a little bit too large, and fragmentation, which is finally, oh, it's an established connection. Ooh, large fragments, I have to allocate memory. Come on. This is not science stuff, this is easy stuff. And the firewall vendors can't get that things right. So what would you expect Windows or BSD or OS X? How good is their implementation? And I've shown you before, it's even worse. So that's the state of security that we have in IPv6 implementation. That's the reason why there is this large difference in IPv4 implementation bugs and IPv6 implementation bugs. There's one more. I call this router alert magic. What is that? Router alert magic? Okay. There is an extension header in IPv6 I find very, very cool, and thank you for having hackers in the RFCs committees putting stuff in we desperately need for hacking. The hop-by-hop extension header is something, if you tell that to a hacker that it exists, they go like, whoa. So a hop-by-hop extension header is, if you put this extension header into a packet, the standard says every router on the path must inspect the packet. So the contents of the packet. So first the extension header, and then depending on what's in this extension header is also the upper layer protocol. And now imagine you found the bug which crashed, for example, a Cisco or Juniper, and just send it on the path, and every router on the internet goes boom, 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 boom. So sounds like a very good idea in my opinion. So there is this extension headers which forces every router on the path to at least look at the extension header, and there's an option called router alert. The router alert option means the upper layer transport protocol is important for you, you must check it. And there are there's another option which says what kind of upper layer transport protocol is. This would be multicast listener discovery, which is an ICMP type, which actually would not be traveling over the local LAN actually, but you can. And what could probably go wrong? It's not a big issue, but it's a surprising issue. If you ping a Cisco router, so this is Cisco, and it has an ACL which says no ICMP from me, guy, yeah? It will not reply because of its ACL. It's preventing receiving the packet. However, if you ping a system which is behind the Cisco router, but put the router alert option in, the Cisco will answer. And this is true for all ICMP version 6 types. Everything. So, with such a simple matter, you can bypass ICMP ACLs on the Ciscos. Again, how could this happen? Come on. They're fixing that now, so Cisco is actually one of my favorite companies to work with because they're actually fixing stuff, especially for IPv6. And they have also a very good IPv6 security team. Yeah, and I want this bug fixed for a reason. When I did my first research, like on router alert stuff 5 years ago, I was thinking, wow, this feature would be a great denial of service tool. I flood a remote network with packets, and they all have the extension action hop by hop and router alert, which would require every router on the path to inspect the packets. So how it usually works, everything is done in hardware, in ASIC, otherwise you don't get any speed. But if there's a hop by hop extension header with a router alert, every router must copy the packet to RAM, and then the CPU must assess the packet. And CPU on a router is a limited resource. It's an expensive resource. So if you flood a router with that, my expectation was, yeah, routing will get very, very slow for the whole path. To my surprise, what happened, that my packet latency was cut by 50% to 200%. And I did a test for, I looked for the most far away server I could find. It was in Japan. To ping and back, it was 1.8 seconds. Then I put the router alert option into the ping packet, and finally it was only 200, 300 milliseconds. I was like, okay, something is going wrong here. I mean, clearly this must be some bug. The remote server can't be sending this data. I mean, there are undersea lines, and of course this must take a long time to get to Japan. So this can't be true. So I went to some friends who had servers, so really their own servers, with IPv6 in some places in the world, and then I said, okay, let me do this with your system, and you TCP dump, and you see if the packet really arrives at your system, and if your system really sent the answer. And we did that, and it really happened. So the answer was really from that system I was pinging. And that's amazing. I mean, I'm from Germany. If you want to do first-person shooters, you know packet latency is very, very important, that your bullets fly faster than the others. And you can pay extra to have a lower latency for your packets. For example, Deutsche Telekom calls that fast path and costs something like €5 per month or so. I get way better lower latency by this and doing it for free. So this is actually pretty nice. However, then Cisco implemented this bug in their iOS. My ISP installed this buggy iOS in their routers, and since then I can't use this feature anymore. So this is why I'm really desperate that this bug gets fixed, and then also the fixed iOS image gets implemented in the routers of my ISP. Because this is really good stuff. Yeah. To a completely different topic. When it comes to IPv6, people seem to think that everything is nice. Like in 1995, when IPv6 was designed, the internet was still a very safe place. You didn't need to encrypt your traffic. Yeah, you could do telnet and HTTP and everything. No encryption necessary because there were no or very few bad people on the internet, which is totally different today and especially in this room maybe. And it seems that the same thinking is now on IPv6 today. So what I did was I got a list of the 2,000 most high-profile domains which are IPv6 enabled. On these 2,500 domains, so New York Times and whatsoever, blah, blah, I did DNS hostname brute forcing, so www.company.com, ftp.company.com, smtp.company.com, and so on and so on. So for several thousand host names. And every time I get back an IPv4 and an IPv6 address for a server, I put these addresses into a special file. When I did that for the 2,500 domains, took quite some time, what I did with the servers, I port scanned them. I port scanned them for the IPv4 address and for the IPv6 address for administrative ports, SSH, remote desktop, and so on. And I was interested, is there actually a difference? And surprisingly, there is. So for servers, on IPv4, you see that, for example, VNC, RDP, or Telnet, is very, very, very rare, 0.1%, that an administrative port is open on IPv4 internet for you. That's a good number. Now, okay, SSH is more dominant with 3%, but this is usually then hosted servers. Let's have a look on IPv6. IPv6 is still not that high number, but if you compare it to this, it's 5 to 6 times the number. So 5 to 6 times more insecure ACL configuration or no ACL configuration on IPv6. Okay, I thought, doesn't look good. So companies don't seem to know that well what to do. How about the ISPs? So at the next step, what I did, I traceroute all these machines on IPv4 and IPv6 and collected the routers on the path, the addresses. And then I did the same thing to those routers from the ISPs. So Telnet, SSH, what's the difference? On IPv4, you see that, for example, Telnet is available on 5% on all the IPv4 routers, where you have 7 to 8% Telnet. I mean, I can understand for IPv4, maybe the router is still old, they don't have SSH support or something because RAM or CPU limitation stuff, I understand. But every device which supports IPv6 has SSH. So I don't understand why there is Telnet on IPv6 devices. I don't understand that. And SSH, you see, it's something like 16%, where it was here 7%. So even ISPs are way more insecure in their configurations on IPv6 compared to IPv4. So you might ask, okay, why? Actually, I think there are two reasons. The first reason is that to protect your environment, you need a firewall. And IPv6 firewalls are scarce. They have very limited support for features. They're expensive, and basically you have to buy them. Buying them in a company takes time, and someone needs to sign off, budget, and stuff like that. So that's why lots of the environment today don't have an IPv6 firewall. They have an IPv4 firewall, and they filter stuff, and IPv6 is unfiltered. I do lots of scanning on IPv6, of course, for statistical purposes. And I really scanned a lot. Every year I scan several hundred thousands of machines. And how should I say that? Very rarely I get an email from the abuse team of my ISP. Very, very rarely. Yeah, there are some common ones who always tell you, and you put them in a list, you don't scan them again. And in my current scans, nobody has a problem. Nobody. I scan really millions of addresses, nobody cares. And from the output you see, oh, no security, wonderful. We come to that in the next slide, don't worry. So the second reason I think we see that is that they are pretty careless on IPv6. It's difficult enough to get IPv6 in your environment running that caring also for security, you don't have the time. And you don't see the need, because who's on IPv6? Nobody. There are no hackers on IPv6, so why do you need protection? Yeah? And that's why you still see Telnet being available on IPv6 devices. Horrible. Yeah. So, final topic, how do I pen test IPv6? The main problem when pen testing IPv6 from remote is that the subnet the servers are standing in have a very, very, very large size. A subnet is a /64 of 128-bit, which means that every subnet in IPv6 you want to scan is 4 billion times the whole internet. So how do you want to scan that? Whoever here in this room scanned the whole internet for one port? I did that, and several people I know did that. Yeah, one hand there. How long did it take you? How many days? The guy who was raising hand, how many days did it require you to scan the internet for one port? Okay, I can tell my number, it's about 12 to 14 days. From one machine, not that powerful, but a very good internet connection, took 2 days, 2 weeks. So if you have better machines and stuff like that and you can distribute a bit, you can get down to 1 to 4 days to scan for one port. Port 80 and some others. Yeah, and it's very noisy and you get lots of complaints, really, really lots of complaints. Dan Kaminsky and Sebastian Kramer, they did, so I did the initial project with Sebastian Kramer together. Dan, because Dan has vast better resources to do scanning than Then Sebastian continued the project with him, and they got lots of complaints, and even suing stuff, and yeah, it was horrible for them. On IPv6 it doesn't happen, but the thing is, if you want to ping scan, a live scan, one subnet only on a remote network, if you start this today, even your grandchildren will not be alive to see the output of that one scan. So this is the main problem with IPv6, target discovery, because the networks, the subnets, are so large. So this is why I will now show you how to do that. Of course, 100% completeness is what you want to achieve, but with that large subnet size, it's not feasible. But I can show you how you can statistically get to 90 to 95% in a very short time. So my thanks go out to the RIPE NCC as acting as my example for all the methods to show you. They know about this part of the talk, and they say, yeah, we know, but actually we are fine with that. So I'm very happy to say thank you to supporting this part of the talk, because every technique I'm showing you works on RIPE. And you will see stuff you all know, and you can't believe that it works. So first, if you want to attack something, and hopefully you're getting paid for that, from your target, not from somebody else, you must find out what is actually their address space. If you know their address space, then you can attack them. You don't want to attack somebody else who is maybe innocent. So the easiest way to do that is to go in the BGP routing table and see what is that address space they are using. You can register IPv6 address space, for example, at RIPE, but usually because they have ideas like, yeah, we will become the largest company in the world, so we should register a very large IPv6 address space. So what they register is very, very large. It's not what they are using. So that's why you should not look for what they have registered, but rather what are they announcing via BGP what they want to have from their large address space. For that, you first need the autonomous system number. This is how you find them in RIPE. You just ask for RIPE NCC in the RIPE database, but there are many other search engines where you find that. You get the results of all the autonomous system numbers. Now the next step is you dump the announcements for these autonomous system numbers. There are enough tools for that. A good one I like is from Hurricane Electric. You just give them the autonomous system number and they show you, this is the IPv6 prefix they want to have routed to their network. You did this for all the four autonomous system numbers you found for RIPE. This is one. One of the autonomous systems has no IPv6, and the fourth one has a lot. You see already /48. /48 is a very large network. It's, if you compare it to IPv4, it's a class A network. So it has 64K possible subnets, which is a lot. And now we have 2, here we have maybe another 16, 18 class A possible networks. And every subnet has 4 billion by 4 billion possible addresses. So that's such a large number which seems unfeasible. But there is stuff we can do. I did lots of scanning, as I already told you. What I found out in the statistic analysis is that there are, from this gigantic large subnet address space, there are addresses which are very commonly configured. The 1 and 2, the 0, 1, 2, these are the most common configured host addresses on a subnet. And they are usually the default gateways, the main routers of the network. So the : 1, which would translate to the .1 in IPv4, is configured in 63% of all active networks. If you go for 0, 1, 2, it's 79%, so roughly 80% of all the networks. So what we can do is we use a tool where we scan the range of prefix they are using and just scan for the host parts 0, 1, 2. And 80% statistically of the networks being in use will show us that they are alive. So this is a very, very quick way where in 30 seconds, you can scan one of these /48 prefixes and see 80% of the networks that are actually being used. So this is very, very fast thing, and then you say, okay, from this large address space, they're using these networks. But there's more you can do. Another techniques you can do is extract everything possible from DNS. In IPv6, addresses are very, very long. There's nothing like who knows the DNS IP address of Google? Hands up. Yeah, 20% I would say. It's 8.8.8.8. Everybody can remember that one, come on. On IPv6, there is nothing like that easy address. So if you know one IPv6 address in the future, you're actually pretty good. Yeah? So everything in IPv6 must be in the DNS. So that is why DNS is a very valuable target for a pen tester. So first we look into the reverse stuff. That is IPv6 address resolving to a host name. And there is something nice in the DNS protocol definition. In that, if you ask for a subdomain, you get a reply back if this subdomain exists or not. And we can use this technique to get the reverse DNS information. So we ask for some part of the reverse IPv6 lookup address, and those where there's nothing below, we get an NX domain error. For where there is something below, we get a no error. And for the whole /48 address space, we can do that until we get down to the reverse DNS name, which then translate to the host name. And this is something which takes about 30 seconds for each /48 gigantic large subnet. So this is very, very, very fast. What we get is possible systems that are alive, possible IPv6 addresses that are being in use, and we collect them. So this is how it looks, for example, for RIPE. Yeah, you see, it's very, very, very fast, and you get all the information out that they have in their reverse zone file. But what you also want to have is the host to IPv6 address relation. There are several techniques for that: zone transfer, DNSSEC walking, DNS brute forcing, hostname brute forcing. The first two rarely work. Zone transfers, how often do you see that a DNS zone transfer works? It's very rare. DNSSEC walking is very nice, but DNSSEC is still very, very rarely deployed. So usually you're stuck with DNS brute forcing, which is still good enough. But if DNS zone transfer work, like on RIPE, you have every information you need. You have 100% completeness of the DNS information. If you do DNSSEC walking, you also get 100% completeness. If they have DNSSEC, like RIPE. If that's not possible, and that's the more common case, then you have to do DNS hostname brute forcing. So having a large word list of possible host names they could have, and then try if that resolves to an IPv6 address. And in the output, you see all the different networks they're actually using. You get possible IPv6 addresses that might be live because they have an entry for that, and you also see the networks they are using. So now we have a list of networks they were using from the scanning we did, from the prefix scanning, and possible IPv6 addresses and networks from the DNS analysis. So we all put that in a very large file, and we have a scanning tool which helps us now doing the live scanning. This I option is for the input file, where you have everything just put in. The D performs a common address scan. This was output of a statistic analysis where I found, oh, how do they configure IPv6 host addresses? And sometimes they are random, sometimes they have various different kind of patterns. And the talk from 2 years ago, 3 years ago, this shows exactly what people configure and how this looks like. Then if they're auto-configured address, this is the options for that. F is a firewall piercing mode, so sending SYN packets to various ports, UDP packets, and so on and so on. And then you go. And then you'll see, wow, 671 systems alive on IPv6 on RIPE. From this search space, which was several trillion numbers of possible IPv6 addresses, with just 5 minutes of work, we found at the minimum 90% of the reachable systems. That's how you do that. You can also create nice network maps. Yeah, my time is up. I can only say lots of IPv6 is broken, not only security-wise, also if you just want to implement it and get it running. So everyone who has to do that, you have my feelings. I have to leave after lunch, so you have any more questions, find me during lunch and ask me there. Otherwise, wish you a great conference. There's the toolkit. Thanks to people who make, like me, software available free. They do picture availables for free to make more nice presentations. Thank you, everybody.